In this lesson, we're going to look at derivatives for trigonometric composite functions. At this point, we should have already watched some videos over the chain rule and then also have completed the decomposition of these functions right here. All right, let's look at finding derivatives for trigonometric composite functions. All right, in the past, we just found the derivative of y equals sine of x, and that derivative y prime was cosine of x. But what happens when we have a more like a composite sine function? It's not just sine x, it might be sine of 5x or sine of some parenthesis. All right, so right here in our first example, y equals sine of u, and we're going to say that u is equal to some other function in terms of x. So I'm just going to put u equals g of x. All it means is that u may be replaced with 5x, or maybe even some parentheses like x squared plus 3. All right, so the first thing we want to do is we want to bring in the derivative operator and find the derivative with respect to x, because that's really what u is being a placeholder for. So we're going to bring in d over dx to both sides of the equation. Now, I would otherwise rewrite y equals sine of u and then bring in d over dx, but I'm kind of limited on space here. All right, so the derivative of y with respect to x is dy dx, or y prime. Now over here we have a composite function. The outside function is sine and the inside function is our u. So this derivative operator tells us that we need to find the derivative of first the outside function. So sine would go to cosine. We leave u alone, but then we're going to multiply by the derivative with respect to x of u. All right, we can take and put the u on top here and just kind of simply be done with the derivative notation. Sometimes you'll see du over dx replaced with u prime, but then again, it's not real revealing that u is in terms of x. All right, so here's our example. Y equals 3 times sine quantity means parentheses, 6x plus 1. So notice that we have a constant multiplier of 3. We have the trig function of sine, and then the u is actually 6x plus 1, or the inside function is 6x plus 1. All right, let's find the derivative. So I'm going to simply go to y prime. I'm not going to bring in d over dx in this step. So y prime means that I need to find the derivative of the outermost function, which is 3 sine of x, if you will. So we keep the 3, it's a constant multiplier. We focus our attention on finding the derivative of sine, which is cosine. We leave u alone. So in this example, u is 6x plus 1, but then times the derivative with respect to x of 6x plus 1. So make sure we have parentheses here, because otherwise without them, it's called a presentation error. All right, so now I'm on this line. I'm going, okay, the derivative operator tells me I need to find the derivative of this linear function. Well, I know that derivative is just 6. So now I can take this 6 and kind of work my way back up to the front and say, hey, let's multiply 6 times 3. So that's 18 cosine quantity 6x plus 1. And that's our final answer. So in this example, we only really had 2 functions. We had the outside function of sine and the inside function of 6x plus 1, and we handled 3 with the constant multiplier rule. All right, let's jump over here to y equals cosine of x. Let's find the derivative with respect to x, because u is a placeholder for some other function that is in terms of x. So dy dx, or y prime. So we have the outside function of cosine. It goes to negative sine. Let's leave u alone, times the derivative with respect to x of the u, and we'll just put the u up here. So often you'll see this written as y prime equals negative sine u times u prime. Just alternate notation. So let's do an example. Okay, and feel free to pause the video, work it out on your own, and then come back and check how you did. All right, I'm going to not bring in d over dx here, and I'm going to say, okay, I'm ready to go to y prime equals 7 times the derivative of cosine, which is the outside function, goes to negative sign. So I'll put the negative in front of the 7. Sign, leave u alone. Here's where we're at, u alone. And then I will show the setup of times the derivative with respect to x of u. I like doing this step because right here is where I can go, oh, I have to evaluate this derivative, and that derivative is -5. So I can kind of evaluate here and then kind of manage at the same time that -5, bringing it, I can't multiply it into this argument, what we call it, but I can multiply -5 times -7. So the final answer is 35 sine of quantity 12 minus 5x. Now, certainly many of you are going to be able to go from the problem straight to the answer, and that's fine. I just kind of like this middle step here because it allows you to kind of eliminate some mistakes that you might do if you make too big of a jump. But it's fine by me. All right, let's look at a tangent composite function. So d over dx, I'll go to y prime this time, equals tangents on the outside, so we go to secant squared. Keep the u times the derivative with respect to x of the inside function. So this is the formula. Let's do an example. Notice the placement of the cube is not on the tangent function. It's actually on what we call the argument. All right, so I'll bring in the derivative operator, which means I'm ready to go to prime. So y prime equals. Now the hardest part over here is figuring out what is the outermost function. What's the last thing that we're going to compute? Well, sometimes it's easier to think about what's the first thing I compute if I knew what x's number was. Well, if I knew what x was, the first thing I would be doing 4x minus 3, getting that answer. And secondly, I'd cube it. Lastly, I'd take that number and find the tangent. So tangent is actually your outermost function. So we're going to take tangent and we're going to change it to secant squared. But I have to keep everything here the same. So 4x minus 3 to the third power times the derivative of what I left alone over here, which is 4x minus 3 to the third power. All right, so now evaluating what I have to find the derivative of, notice we have another composite function. We actually, in this example, have 3 functions, so it's going to be a little more complicated than these previous 2 that only had 2 functions that, 2 parts that made up the function. All right, so this derivative, well, the outside function now is x cubed. So 4x minus 3 is the inside. So let's find the derivative of, thinking in our brain, x cubed. So actually on this one, I'm not going to cross it off with an arrow because I'm going to need more room. So keep secant squared, squared's on the secant function, 4x minus 3 cubed. Now let's take care of this derivative on this line. All right, so the derivative here of this expression would be to pull the 3 in front, keep 4x minus 3 the same, but drop the 3 to 2. So think of 3x squared times, we did that derivative, but we still have to find the derivative of 4x minus 3. Now here on this line is where I'll go, oh, this is an easy derivative. That derivative is 4, and I'll manage that 4 by coming up and grabbing it with a 3 and getting 12, and then bringing the 12 all the way up to the front. So I have 12 secant squared, quantity 4x minus 3 cubed. I took care of the 3 already. And then what I have is times 4x minus 3 squared. I'm going to actually rearrange this because it's not wrong to put this binomial square behind, but it almost looks like I want to multiply it into the secant squared's argument here, and that's not true. So I'm going to do y prime. I'm going to put the 12 first, and then I'll bring up the 4x minus 3 squared, and then I'll jump back in and write secant squared. It just looks better. It's just more clear that way. Okay, let's do cotangent. So we'll bring in d over dx. So y prime, derivative of cotangent is negative cosecant squared. Leave the u alone and take and find the derivative with respect to x of u. So here's our example. Okay, let's find the derivative. So the prime equals, the outside function is cotangent and the inside function is x squared minus 3x. So there's only two functions that compose this y. Derivative of cotangent is negative cosecant squared. Leave x squared minus 3x alone. And then let's get the setup times the derivative of x squared minus 3x. And again, be mindful of these parentheses, because if you didn't have parentheses, it's almost like you're saying just find the derivative of x squared and not the minus 3x. And again, that's called a presentation error. You know what you're going to be doing, but the math doesn't make sense. All right, can I go ahead and cross this off? I sure can. This derivative is 2x minus 3. And I'm going to think about not leaving 2x minus 3 behind this quantity. I'm thinking about pulling it all the way up behind this negative sign. So I'd have negative 2x minus 3, and then return to the cosecant squared piece of this. No, you do not have to distribute that negative in. It's better just to leave this answer in completely factored form. Okay. All right, let's look at secant. So bringing in d over dx. So y prime equals, now the derivative of secant x is secant x times tangent x. So the derivative of secant u is going to be secant u times tangent u. That's the derivative of the outside function. The secant times the derivative with respect to x of the u. And this may be 5x in both these u positions here. So that derivative would come last. So let's do an example. So all of this linear function is our u. So let's go to the prime. We have another constant multiplier, so I'll just keep the 7. We want to focus on the derivative of secant u. So that's secant 5x plus 3 times tangent 5x plus 3. And then don't forget the derivative of 5x plus 3. This derivative is easy. It's just 5. I'll think about how do I want to place that 5, probably all the way up front, multiplying it with the 7. Okay, and the last one. All right, cosecant of x's derivative was negative cosecant x, but we'll use u, times cotangent of u times the derivative with respect to x of whatever that inside function is. Okay, I see negative 5 as a constant multiplier, so I can really focus on just cosecant's derivative. So y prime equals, cosecant's derivative is going to be negative, so multiplied by another negative would be positive 5. So cosecant cotangent. This derivative is easy. It's 8. I'll manage the 8 with the 5, multiplying together. So that's finding derivatives for trigonometric composite functions.